All right, so I've set up a pretty involved problem here. So what we have is we have some wire rails with a bar that can slide on it when it's pulled inside of a magnetic field. And so this bar is being pulled to the right. Someone's applying a force to pull this guy to the right at a constant speed of 2 meters per second. So, and then we have the magnetic field strength is going to be 200 milliteslas. The resistance of our bar is 10 ohms. We'll say the wire itself is ideal and has no resistance. And that the length of this section of the wire is going to be 10 centimeters or 0.1 meters. So I want to know several things on the right here. So the first thing I really want to know is what is the direction of the induced current? And I can do that without doing any math, right? I can say, I can say that as we pull this bar to the right, are we increasing or decreasing the flux through the loop? Well, if I pull this bar to the right, now the bar is here, let's say. We'll say the bar is here now. So now do I have more or less x's inside my area, right? My area is increased. The magnetic field hasn't, but my area is increased, so my flux is increased. So my flux in this direction has increased. So my my current I'm going to produce is going to oppose the change. It wants to reduce the magnetic field. So it's going to create a magnetic field pointing out of the page. So to do that, I want my current to be flowing in this direction. I want to go counterclockwise here. So I'm going to draw my current on there and say counterclockwise. So part A, we are going to say counterclockwise. Write that down for you guys. All right. Part B, it wants to know what's the magnitude of the induced EMF. Okay. So for part B, I need to solve the Faraday's law. So it's going to equals N times the rate of change of my flux. So the real tricky part here is going to be figure out the rate of change of my flux because we know it's N. So we also know this should be a minus sign, but it says magnitude, so I don't really care about that because I'm going to say magnitude of this, magnitude of that, put some absolute value signs around it. So how do we find the flux? Well, we said flux is going to be magnetic field times the area. Well, what's the area of this loop is changing, right? So it's as this guy goes to the right. So the area is going to be this length going this way, right? Times the width of this loop. Well, the width of this loop is going to depend on the speed. So it's actually going to be velocity times time. Probably plus a constant, but since we're looking at change, I'm not going to care about that constant anyways. So that's my flux. So we'll say V delta T just for demonstration purposes. Okay, so I can find my flux that way. So now if I want to find my EMF, what I need to do is I'll say it's the magnitude of the EMF is going to equal to 1, because there's only one loop, times this over delta T. So it's going to be BLV delta T over delta T. So my delta T's immediately go away. And so the EMF I am generating is going to be the magnetic field times the length times the velocity. And if you guys can follow, want to do the math with me. So my magnetic field is 0.2 teslas. The length is 0.1. So I like to put all these in parentheses just so you know where things began and where things ended when I substitute n, and the velocity is 2. So this is going to be 0.02. I multiply those guys, so 0.04 is my EMF. 0.04, and the unit of EMF is volts. Oh, went off the screen a little bit. There you go. So that's part B. So now C is going to be, what is the magnitude of the induced current? And if you guys know that if I have a circuit and I know the resistance and I know the voltage, it's going to be real easy to find the current. So I'm just going to use Ohm's law. I'm going to say V equals IR, or in this case, we could say EMF because they're basically the same thing. So to solve for the current, I'm going to say I is equal to EMF over R, and we know R is 10. So my current is actually going to get smaller. Oop, you got off the page again. You need to keep a better eye on that. So I is going to be EMF over 10, so 0.04 volts over 10 ohms is going to be 4 times 10 to the negative 3 amps, or 4 milliamps. So not too big, pretty small. But we're in good shape so far. Okay, so now power dissipated. So these first three parts are the part that's going to be really important to the AP exam. I decided to go a little bit farther with this because you never know what they're going to take it, especially this year since everything's going to be so weird. And besides, this will be very important for Physics C when you guys do it next year. So the power dissipated, well, you guys should know the power equation from when we did circuits. So let's do part D here. That's the D. Unit power is IV, or I squared R. I'm going to use I squared R in this case. I could use IV, it doesn't really matter. So I just like I squared R. So I mean, we're done. We just need to put the numbers in. So the power is going to be 4 times 10 to the negative third, because when you're working with metric multipliers, you really should get rid of them and put them back into the base level. Otherwise, I'll square it and get 16, and I'll have a problem because I won't have considered this negative 3 up here. So 4 times 10 to the negative third amps squared times 10 ohms. So that is going to be, well, 16 times 10 to the negative 6. So 1.6 times 10 to the negative 5 times 10. So 1.6 times 10 to the negative 4. And power, well, watt is the unit of power. Been telling that joke all year. All right. So then lastly, in part E, if I want to know that force, because someone had to apply a force to this wire to make it move, right? Or to this bar. You can't just say, hey, it's going to move. It's going to take a force to do this. Especially if I'm losing power to heat, that'll be like, because this would be the power I've lost, how much energy I'm losing per second to heat dissipated in this loop, right? But that, because energy is conserved, that energy has to come from somewhere. If I'm going at constant speed, all of the energy I'm giving to the bar is going to heat. So a nice equation I can use for this is I can say that power equals force times velocity, right? And I'm using the curly V for velocity here, just so you don't think it's voltage. I should have used it above, but kind of forgot. So I know velocity, I know power now, right? So I can say force is equal to power over velocity. At this point, we just put our numbers in, and I get power is 1.6 times 10 to the negative 4. Watts. Velocity we said was 2 meters per second. So that is going to get me the force is equal to 0.8 times 10 to the negative 4 newtons, or better written as 8 times 10 to the negative 4 to the negative 5 newtons. All right, we're going to call it good for this one, and see you guys in the next video.